Hello everyone. I have done a couple of problems on mesh analysis in my previous videos. I thought this problem might interest the viewers in the sense that this problem is slightly different from the other problems that I have recorded and uploaded. This problem has coupled circuits. We are supposed to write the equilibrium equations for this particular network based on mesh analysis or based on mesh basis for the network which has coupled coils or coils which are coupled to each other. So here in this particular figure, if we can see, there are three inductors L1, L2, L3, wherein L2 and L3 are coupled to each other. There is a mutual coupling coefficient that exists between L2 and L3. That means a current through L2 will produce an EMF in L3. Similarly, the current through L3 is capable of producing an EMF in L2. They can be in fact treated as dependent sources. The EMF that is induced in L2 and L3, they depend on the currents in L3 and L2 respectively. So in order to solve problems of this nature on mesh basis, we need to have a clear understanding of KCL, KVL. Of course, that happens to be the fundamental requirement, KCL, KVL, and how to write mesh equations by inspection. This knowledge is helpful. And another important knowledge that is helpful in dealing with problems of this nature is dot convention. These are the prerequisites. I have my videos wherein I have solved problems of series parallel networks wherein the concept of KCL and KVL gets demonstrated. I have videos wherein I have solved some problems on mesh equations or analysis of networks based on mesh currents. But then I have not made any specific video for dot convention. Actually, if we look at the dot convention, it is a standard practice to place a dot on one end of each coil if it is mutually coupled with the other coil. A dot indicates the polarity of the EMF induced in a coil due to the current in the other coupled coil. Alright, so how do we understand this dot convention? A brief, a side note to the dot convention I would like to quickly go through so that you will be able to apply that to the coupled coils. If you have two coils which are of this nature, just a quick look at the coupled coils. See, let us say that these two are the two coupled coils having inductances L1 and L2. They are coupled to each other. That means there is some amount of mutual coupling between the two. So let M be the coefficient of mutual coupling between L1 and L2. Okay. So the currents in these two coils are capable of producing EMFs or fluxes. Alright. So we need to know the direction of winding of the coil on the limbs of a core or something, if it is a iron cored inductor. Okay, if you imagine an iron core inductor, could be a transformer for that matter. If you have two coils which are wound at the limbs of the inductor, it depends on the direction of winding. The flow of current in these windings are capable of producing either aiding fluxes or opposing fluxes. So not always it's possible for us to look at the winding. So in order to simplify things, transformer windings or your coupled windings are assigned polarity markings in terms of what we call as dots. Dots are typical symbols. Okay, there can be a circle, they can be put as a rectangle or a square and a triangle and things like that. In general, all these shapes are referred to as dots. Okay, you don't say triangle, you don't say square, etc., etc. You simply say dots. Okay, so if you have similar symbols near two coils, it means to say that these two coils are mutually coupled to each other. That means current through one coil is capable of inducing a voltage in the other coil, which is similar to a which is nothing but a dependent source. All right. So now we need to know two things here. One is what is the magnitude of the voltage that gets induced. Another is what is the polarity of the voltage that gets induced. All right. So according to dot convention, what we understand is if the current enters the dot in a coil, I shouldn't have erased it. Anyway, let me quickly write. It doesn't take much time. This is my L1, this is my L2. Let us put a dot here, and this coil L2 has a dot here. Okay, this is the polarity marking that I have for these two windings. All right. So if my current through L1 is flowing in this direction, that is from the dot towards the undotted end, or in other words, I1 is entering the dot and leaving this way. Okay, and similarly and simultaneously, if I assume another current I2 to be flowing through L2 such that I2 enters the dot and leaves the undotted end. Okay, here in both the coils, this is the dotted end, the top is the dotted end, and this is undotted end. Here also, top is the dotted end and bottom of the coil is undotted end. That's how we identify. Okay, if the currents in both the coils enter the dot simultaneously, or the other option is or if the currents leave the dot in both the coils simultaneously, what I mean is the other case is L1, L2 is like this. My dots are supposed to be, suppose they are present here, my current I1 is entering here and current I2 is simultaneously entering at this particular end. Now I1 is leaving the dot and I2 is also leaving the dot. Okay, the situation is here currents in both the coils enter the dots simultaneously. Okay, here in this case currents in both the coils leave the dot simultaneously. Under both these circumstances, the fluxes or the mutually induced EMF aids the self-induced EMF. Okay, this is the basic summary. Now, if we have to understand this little more precisely, then how do we exactly understand it? See, when the current enters the dot in one of the coils, then it produces an EMF which is positive at the dot of the other coil. I'll repeat, when the current enters the dot in any one coil, it produces a mutually induced EMF in the coupled coil which is positive at the dotted end of the coil. This has to be very clearly understood. This is what the dot convention is supposed to mean, and we need to apply this concept to the coupled circuit. Alright. At the same time, if the current leaves the dot, instead of entering the dot, if the current leaves the dot, then the induced EMF will have a negative polarity at the dotted end. That's all we need to understand. That's all we need to remember. If we can remember this much, we can apply and proceed. Okay, there are only two things. One, current entering the dot, another, current leaving the dot. Alright, when the current enters the dot, it produces an EMF which is positive at the dot of the other coupled coil. If the current leaves the dot, instead of entering the dot, if the current leaves the dot, then it produces a negative polarity at the dot of the other mutually coupled coil. That's all. That's all we need to understand. We need to remember rather. Okay, if we can remember this concept, we will be able to apply. Now let's go to the problem. Okay, I'll see if I can make a video to this separately and then upload. Otherwise, as of now, this is sufficient. The understanding of this is sufficient as to how to apply or how to understand the polarity using what we call as dot convention. Alright, so you need to know KCL, KVL, you need to know how to write mesh equations by inspection, and the third requirement is that you need to understand the significance of dots in coupled coils. Alright, so we will see. Now if we can look at the network, this is an independent loop. This is loop 1 or mesh 1. This mesh 1 is an independent mesh. There is no electrical connection between mesh 1 to, this is my mesh 2 and this is my mesh 3. Okay, mesh 1 is electrically isolated from mesh 2 and mesh 3. There is no electrical connection as such. Of course, mesh 2 and mesh 3 have certain elements in common. They are electrically connected. Alright. However, you are able to see that mesh 1 is coupled to mesh 2. What we mean to say is, current through the inductor L2 is capable of producing an EMF in the coil having a self-inductance of L3 because they are mutually coupled. Alright, so we will now go ahead. As usual, like how we do other problems of mesh analysis, we have assumed clockwise currents. The three clockwise currents are I1, I2, I3 respectively, in mesh 1, mesh 2, mesh 3. Now let us try to write the equations. Okay, let us try to write the equilibrium equations for mesh 1. How do we write? It is simple. We start from, as my practice, as I normally do, I start from this particular top left corner. This point I'll start from A, go through L1, go through L2, come back to V1, come back to R1, then back to A. Okay, top left corner I'll start. Okay, so I will write the equation, equilibrium equation. Let me write. Okay, so the equilibrium equation is, what is the self-inductance in L1? That's self-inductance is L1. So when the current flows through that L1, the coil, it produces a self-induced EMF. What is the magnitude of self-induced EMF? It is simply L1 di1 by dt, because I1 is the current through L1. So L1 L di by dt is the EMF induced in an inductor. Alright, so L1 di1 by dt, that will be the first thing. And if we come to the second, that is inductor L2, we can write it this way, plus there is an EMF L2 di1 by dt, that is the self-induced EMF in L2. Now there is another EMF, a mutually induced EMF in L2 because of the current that flows through L3, because L2 and L3 are coupled. Okay, the current through L3 will produce an EMF in L2. So what is the magnitude of the EMF? The magnitude of the EMF is mutually coupling, coefficient of mutual coupling M, and d by dt of the current that is responsible for this mutually induced EMF is I2. Okay, the current that is responsible is I2. So m di2 by dt is the magnitude. Now this m di by dt, should it be taken as plus or minus is the question. So what determines the sign or the polarity of the induced EMF? It is the dot. Alright. So we need to now see that this mutual induced EMF is due to the current I2. And now we need to look at this particular current I2, whether it enters the dot or leaves the dot. Now look at I2. I2 is a clockwise current, which is very obviously, it's evident that it flows in this direction. From bottom to top in L3. Alright. From bottom to top in L3. So while going from bottom, it enters the dot. Okay, current I2 enters the dot in L3. When the current enters the dot, according to our convention, it produces a positive polarity at the dot of the other coil. So other coil is L2. I'll write it here separately. This is L2. Where is dot? Dot is here at the top end. So when it comes to the question of EMF, the EMF that is produced in this, if I can show it as a dependent source, it will have a positive polarity at the top, negative polarity at the bottom, and it has the magnitude of m di2 by dt. Alright. So this is how a dependent source can be imagined, and this is how my L1, this is how the network can be imagined. So in the clockwise direction, if I see, I am hitting a positive to negative. That means a drop in potential, and our convention is drops are taken as positive. And now that is plus m di2 by dt. This is the mutually induced EMF in L2 because of the current through L3. So the magnitude is m di2 by dt. The polarity is the top end is positive, the bottom end is negative, because there is a dot at the top end of L2. And now I will have to now continue. Okay. So we have finished with L2. We have taken self-induced EMF. We have taken mutually induced EMF. Then we come back to the source. Source, I'm encountering the negative sign, minus V1 of t plus R1 into I1 of t, rather I1, which is equal to 0. This is the equation. Alright. This is how we write the equation. You can even write it by inspection. That would require little practice. Okay. If you don't have practice, it is best to take the potential differences across each element and then add it up. That is the best way to do. Okay. Now grouping the terms, we can even write this as, now let's group the terms. That means what I mean to say is, I will group the terms containing di1 by dt. Alright. So if I can group the terms, what is it I get? So I will get R1 into I1 plus L1 di1 by dt plus L2 di1 by dt. Okay. This is one set of terms. And there is another term, that is plus m into di2 by dt equal to V1 of t. This is my one equation I have. But every time writing di1 by dt, di2 by dt is little laborious. So what we tend to do is, we tend to replace d by dt by what we call as a p operator. In my videos, I tend to use this. D by dt, I replace it by what I call as a p operator. I replace it by p. Okay. So I will rewrite these equations as, I will write it as R1 I1 plus L1 p into I1 plus L2 P into I1 plus M into P times I2 equal to V1 of t. I can group the terms now containing I1. All these three have I1 in common. So I can write this as R1 L1P plus L2P into I1 plus M into P into I2 equal to V1 of t. This is how we arrive at one equation. Okay. Now we need to write another equation. For I2, you have three unknowns, I1, I2, I3, so you need to have three independent equations. Now we need to write it for mesh I2. You can write by inspection, you can write by first principle. Here again, in mesh 2, I would start from top left corner. Alright, so if I apply top left corner, then I encounter the capacitor for mesh 2. So how my equations are written? So for mesh 2, this is for mesh 1. I will take a different color. Maybe I'll write this for mesh 1. Okay, now we will write another equation for mesh 2. How to write an equation for mesh 2? So if I start from top left corner, I encounter a capacitor. What is the voltage induced across a capacitor? It is 1 by C integral I dt. What is the current that the capacitor carries? If I start from the left and move towards the right, then the current flow in the direction would be I2 minus I3. This is the current that the capacitor carries. Okay, current I2 is flowing from left to right, I3 is flowing from right to left, and we are moving from left to right, so the current is I2 minus I3 into dt. This is the potential difference that gets created across the capacitor, with left hand being positive, right hand being negative. What I mean is, it's like this. This is the capacitor, positive, negative. This potential difference is now 1 by C integral I2 minus I3 into dt. Whereas I3 is this way and I2 is this way. And you write the potential difference. Alright, that is how the voltage is developed across the capacitor. Okay, now we are done with the capacitor. Now we come to the source of V2, and we hit the potential positive. So positive to negative is plus V2 of t. Then we come to L3. So we write the self-inductance, self-induced EMF first. So I will write L3 d by dt of the current that it carries is I2. This is the self-induced EMF. Because L3 is coupled to L2, there is going to be a mutually induced EMF in L3. What is the magnitude of that mutually induced EMF? So the magnitude of the mutually induced EMF is M into dI1 by dt. Alright, that is the magnitude. It is the I1 current while flowing through L2 which produces a mutually induced EMF in L3. So the magnitude is M into dI1 by dt. Now, should it be positive or should it be negative? How do we determine? We have to look at the current which is responsible for this EMF. What is the current? It is I1. So now we need to look at this current. How does this current flow? If you look at I1, you have to find out whether the I1 current enters the dot or leaves the dot. It is simple. I1 current is seen to be entering the dot. When it enters the dot, it will produce a positive sign at the dotted end of the other coil. That means in L3, dotted end is at bottom, and it is going to be, the EMF is going to be positive here. If this is L3, the EMF induced will be of this nature. Positive, negative. Okay, so the downward is positive. So when we go in the clockwise direction, we hit positive first, then negative. Positive to negative is drop in potential. So drop is taken to be positive, and this is now positive. So you need to put proper polarity and proper magnitude for the mutually induced EMF, and you have come back to the starting point, so that is equal to 0. We will try to rearrange this equation. We will try to substitute again d by dt. We will try to replace d by dt by p, and we'll try to put 1 by integral dt to be 1 by p. We'll make this particular substitution. This substitution helps in, making the equation appear simple. Okay, so we'll try to do that. So this is going to be 1 by c into p, because integral I have removed, I have put it as p, and this is my I2. I am opening up the bracket, 1 by cp into I3 plus V2 as it is of t plus this is L3p into I2 plus m into p into I1 equal to 0. Alright, so I'll group the terms in this equation. How do I group? My first coefficient I have to write for I1, so I'll write this as m into p into I1 plus I'll group the terms containing I2. There is one term here, there is another term here, so that will be, if I write it properly, it will be L3p plus 1 by cp. This whole thing is I2. Okay, there is one more term containing I3, that will be written minus 1 by cp into I3 equal to this V2. I will send it on to the other side, V2 of t. This is my second equation. Alright, so my first equation is this, my second equation is this. Now we will look at mesh 3. We will write equation for mesh 3. Okay, mesh 3 equation. How do we write mesh 3 equation? We will again start from top left corner. So I go via R2. So R2 will develop a potential difference of R2 into I3, isn't it? It is, because the current is I3. This is R2 into I3. Then I have this capacitor. Capacitor will produce 1 by C integral I dt. What is the current through the capacitor? Current through the capacitor is I3 minus I2 in the direction of right to left, which will produce a drop in potential into dt. We come back to the starting point equal to 0. I'll do the same substitution. For integral dt, I'll put 1 by p. Okay, then I'll group the terms. I will write it as R2 I3 plus 1 by cp, this into I3 minus 1 by cp into I2 equal to 0. So I can rearrange these things. I'll write the coefficient of I1, I2, I3. So there is no I1, then I have only I2, 1 by cp into I2 plus R2 plus 1 by cp, whole thing multiplied by I3 equal to 0. This is my third equation. Alright, so we are able to write 3 equations for this particular circuit arrangement. Okay, so it's absolutely simple. It's absolutely simple. There is there's nothing complicated about dot convention. All you have to know is whether the current enters the dot or current leaves the dot. That's all. Okay, I suppose this is simple and easy enough. So in the next video, maybe we will try to see more coils and little complex coupling, that kind of arrangement we will see. Here we are able to see only a pair of coils which have coupling. Here, as we can see, L1 is not coupled with anything, but L2 and L3 are coupled. Similarly, if you have L1 and L3, being coupled and the different possibilities, the network becomes little complicated and one has to be little careful. That's all. Okay, hope this video is helpful in understanding as to how to write mesh equations when you encounter coupled coils. See you in my next video. Thanks for your viewing. If you have any difficulty or any comments, you should feel free to put it in comment box. Okay, thank you.